Okay, well, thanks, Tom, and the Better Plants, Better Buildings program for the opportunity to speak with you today about industrial heat pumps. First, let me acknowledge my co-workers here, Paul, who you've going to hear about shortly, Andrew Hoffmeister, and Riaz has also joined us. So glad to see the team here. So I'll just note that this is part of our work at ACEEE to find ways to lower barriers for low carbon technologies to help industry decarbonize. We do three things in that space. We help to lower hurdles. We work on business practices such as strategic energy management. And as Tom noted, we also work on policies to help encourage low carbon technologies. This is an outgrowth of work that we had done on beneficial electrification. And at the end, we'll have some references both for this report on industrial heat pumps as well as the beneficial electrification report. So with that, let me also acknowledge our sponsors of this research, 4 utilities that have stepped forward to support our research looking at prospects for industrial heat pumps. We appreciate their generosity. I'm going to cover 6 topics today. As you can see on this screen, I'll give you a little bit of background of why we worked in this space, what we found in our study, which industrial groups we looked at, as well as the results. And I'll highlight the energy and the greenhouse gas impact. Certainly that's important as people are thinking about routes to decarbonization and routes to reach their corporate sustainability goals. It's one thing to have the CEO announce goals. And of course, it's another thing to find out how to reach those goals. This will be one of the solutions in the portfolio that you should think about. I'll talk about hurdles just briefly, introduce the question, is IHPs right for the application? And then show a little bit of information about the commercial status of industrial heat pumps. Well, why industrial heat pumps and why now? 2 principal reasons. One is, as I mentioned, corporate CEOs and others are looking for routes to significantly reduce their energy and their greenhouse gas footprint. One of the best routes, early routes for that, is energy substitution. And in this case, I'll highlight beneficial electrification, beneficial being the key word, meaning that the generation of electricity helps to lower the energy and the greenhouse gas footprint that the environment sees, such as through low carbon routes, such as wind, solar, biomass, et cetera. 2 other things to note here is there have been a host of technology advancements in this space. I just note simply working fluids, compressors, and heat-activated heat pumps, but there are more advances as well. And Tom on his slide talked about bonus points for non-energy benefits, and there are a number of those in this space as well, such as improved control of the temperature delivery, speed of response, et cetera. So it's not just energy and greenhouse gas benefits, but there are others as well. So let's talk about the footprint of industry just briefly to get all on the same page. Industry accounts overall for about 22% of the greenhouse gas emissions, CO2 emissions in the US. Manufacturing in particular talks about 16% of that. And if you look at the blow up on the right-hand side, you'll see that chemicals, pulp and paper, and food account for a very good portion of that. And the examples that we'll show you come from those 3 industry groups: chemicals, paper, and food. Well, as Tom mentioned, process heat is the big opportunity in this space, especially early on, because process heat accounts for over 50% of the on-site energy spend in industry. But process heat comes in different temperature ranges. As you can see here on the left, there's some of it that's under 80 degrees C, some that's higher at 180 to 150, somewhere's on up the 300 degrees C. And you can see across different industry groups, the proportion of that process heat by temperature varies. For industrial heat pumps, the target on the upper end used to be 80 degrees. Now I'll tell you that it's upwards of 160 degrees and it's pushing higher. So industry groups of particular interest in this case are chemicals, because they have a fair amount of that process heat that's under 150 degrees C. Pulp and paper, you can see as well. And then, of course, the third one here is food. Those are the three groups that we looked at. But you can also see that refining has some interest in this space as well. Now, you might ask, what are the type of applications that process heat uses? And you can see there it's a fluid heating and distillation, a lot of drying. You can see across these industry groups, calcining, metal smelting tends to be for the higher temperature ends. So we'll be particularly interested in the fluid heating, distillations, drying, evaporations, and for food, it's pasteurization, sterilization, etc. So there's several different kinds of heat pumps. I'll not get into this in detail, but note that there's more details in the paper that we released a couple of weeks ago. There's basically open source heat pumps as well as closed cycle heat pumps. And there's several different varieties underneath those as well. And you can see that there are some that are now waste heat driven as well, which is particularly interesting. Now, if you look at the ranges of these heat pumps, you can see that there are some in the lower temperature range. There are the high temperature heat pumps, and then there are the very high temperature heat pumps that again are pushing now 160 degrees C. So that opens up a wider range of applications in industry than previously was available when the limitation was 80 degrees. Some of this is due to new working fluids, as well as compressors and other advances, as I mentioned earlier. So just a couple of basics here. I'll note on the top, you'll see that in a conventional system, you've got a steam boiler fed by fossil fuel. For an industrial heat pump, there's a number of changes. Instead of a steam boiler, you have a heat pump. Now that can be fed either by electricity or by waste heat. And instead of having an efficiency of about 80%, 90%, we talk about coefficient of performance in this case. That is, that the energy that you put into it, you can actually get more energy out. And in fact, that ratio can be upwards of 4, 3, or even higher in this case. A couple other changes to notice as well is that the CO2 emissions are dramatically different. In fact, there's some 66 to 100% lower for heat pumps. We'll talk some more about that here in a little bit. So what you can do with a heat pump is you can recapture some of the heat that's available in your systems. You can recycle some of that, and importantly, you can boost it into a range that is more useful for work in this case. So let's talk about the industrial heat pumps that we studied in our case. And again, we chose these three areas because they're relatively high proportion of low temperature process heat. And I'll also point out that we chose to examine these applications at the unit operations level, where there are physical changes. We did that for very specific reasons, such as we really wanted to be able to engage folks to think about the applications at the level where they're talking about speccing different types of instruments, different types of equipment at this point. And there have been very few studies at the unit operations level as well. So the three areas we chose were paper, and you can see that in each of those we have three different unit operations. Paper, we had the pulp mill digester, the multi-effect evaporator, and the non-integrated paper mill pulper. We also looked at food and chemicals. Those are the three industry groups that we had looked at. So I'll give an example for an area that we can all relate to, since it's just after lunchtime, and that's food. In this case, let's talk about potato drying. Again, this is something that we can all relate to relative to potato chips, go through this type of processing. Just a couple of notes of impact. 3% of US CO2 emissions are associated with potato drying. Some 49 million tons of CO2 emissions, about a fifth of the industrial process heat as well, is used for this type of application across all of industry. And there are many unit operations in this potato drying that are under 150 degrees C. Again, that's the sweet spot for industrial heat pumps today. And I'll note that there's a portion of the process that's used for hot air drying, and that's the portion that we had looked at. What we found, as you can see in the lower right-hand side, is that industrial heat pumps across the three MVC cases can save upwards of 11% of the natural gas used in these systems. Now you can also see kind of the tan or the brown bar, orange, I guess, and that is that, well, as you displace natural gas, you need electricity to run the heat pumps, but it's a relatively small amount of electricity that you're adding relative to the amount of natural gas that you save. And CO2 reductions in this case can be upwards of 25%. So that's significant as well. So moving on, what's also important is the payback for industrial heat pumps. Now, there's lots of economics that could be looked at here. We looked at simple economics, the rate of return compared to the capital cost of the equipment. A couple of things to point out on the right-hand side is that you can see that the payback is under 2 years in several cases when the natural gas price is higher than $6 per million BTUs. So we're close to that range today. So that means that industrial heat pumps could be at, near, or under 2 years for a payback. We chose 2 years to highlight because that's a typical threshold of interest within industry. I'll also point out that you can see some variation in the payback. When the natural gas price is very low, there's considerable spread relative to the electricity price and the payback. But when the natural gas price is very high, the influence of electricity price is a lot lower. That's because of the fact that there are a number of other factors that come into play that have greater weight at the higher natural gas price, as I pointed out in the last bullet there. So looking at just a little bit more here, if we look at the impact across all facilities in this case, you can see that the natural gas savings, this is the energy savings, the upper right, in trillions of BTUs across the 3 unit operations we looked at. For the potato drying, it can be significant, up to 15 trillion BTUs per year. Now the wet corn milling and the wet corn milling for the high fructose corn syrup are also important, but you can see that the total amount of TBTUs is less than that for potato drying. But if you look at the savings on a percentage basis for the process, you can see that it's higher for the wet corn milling for the high fructose corn syrup. Well, what's the impact that we're talking about here? Upwards of 15 to 20 trillion BTUs for natural gas savings, about 0.6 million tons per year of CO2, and also needs a little bit of electricity on the order of 4.3 trillion watt hours per year, or trillion BTUs. They're somewhat similar in this range. So I mentioned that although natural gas goes down, electricity goes up. And so a question you might ask is, well, what's the difference between the two? And does electricity go up as much as the natural gas saved? The answer is no. You save a whole lot more natural gas than the electricity goes up. Natural gas here, the reduction is in the red, and the electricity increase is in the green. This is for the the energy spend. If you look at the CO2 as well, it's the same kind of story. In this case, the green bar is a bit larger. This is for electricity coming from the grid. And of course, as the grid becomes greener, the amount of the green bar in this case will decrease, and your CO2 reductions there will increase. So industrial heat pumps from a CO2 perspective then get a lot better as the grid becomes greener. Looking at the energy savings and the impact across a couple of other metrics here, if you look across all of the unit operations for food, paper, and chemicals, and you total those up, you could see that one could approach the energy savings of that of 3.3 million homes. in the CO2 reductions of some 9 million cars. Again, the CO2 reductions will go up as the grid becomes greener. Now, one of the key hurdles that we ran across in this space for adoption is the relative price of electricity versus natural gas. And in fact, that varies considerably across the US. On the right-hand side, you'll see the ratio of the industrial electricity price versus natural gas. And you can see in regions of the country where, for example, there might be a fair amount of hydro, Washington State, for example, and New York State, this ratio is favorable for industrial heat pumps at the moment. That is, the ratio is under 4, and in some cases it's under 3. Now, that doesn't mean it's going to be a slam dunk on the economics for industrial heat pumps, but at least you have simple economics that are good enough to start with in this case. This price gap is an area that is an opportunity for policy. So let me just point out the results here for the paper digester. And again, you can find more information in the report. In this case, to reach 2 years of payback, depending on the price of natural gas, you can see that on the y-axis here, we may have to add a certain amount of an incentive for the capital. So when natural gas is $3.2 per million BTU, for the MVC case, you can see that, well, starting out at $4 per million BTU, sorry, a ratio of 4 on the electricity versus the natural gas price, you can see that, well, we don't need an incentive there, but as that ratio climbs, we're going to need an incentive. And in fact, for the other heat pumps, for the MVR semi case, as well as the MVR open case, you can see that a considerable incentive is going to be needed, upwards of 70% in this case, should that ratio climb towards about 8. The reason why we point this out is that this is an opportunity for policy. Policy can make a big difference here to accelerate adoption of industrial heat pumps through multiple areas. It can help defray that difference in electricity versus natural gas costs. You can see that it also can support demonstrations and pilots. It's really important since there haven't been demonstrations of the newer IHPs within the US that we drive those pilots and demonstrations. And in fact, that's our next stage of research to do just that. Industrial clusters are also important, and policy can make a big difference there. Clusters are regions where industry is concentrated. Think about the Houston Ship Channel, for example. That's an area where there can be a lot of communication amongst industry. Should there be a pilot, a number of people can see the benefits and can think about integration of the industrial heat pumps as well. It's also an opportunity to train a skilled workforce because the ability to maintain, the ability to do the integration for industrial heat pumps is an area where we need some skills development. In this case, what we call the middle layer needs to be developed in the US. At this point, we wanted to give you some information on the status of industrial heat pumps globally. So I'll invite Paul to take over at this point and describe the status in a couple of slides. Paul?
Yeah, thanks, Ed. And Riaz, if you want to chime in too, please do. Could use your expertise. So let's give credit to where this chart comes from. Cardin Arpicus from Switzerland is, in my opinion, if not the world expert in industrial heat pump. He's one of the top 3. And he has a number of great references, and this is one of them. And, you know, the state of affairs in industrial heat pumping is in Europe and Japan. We have found that there Johnson Controls, which is not only the US, Europe, does have some US positioning of product line. But as you can see from this chart, the technology. In this case, it has been demonstrated in Japan, primarily in steam applications. And we're looking at different working fluids, yes, but we're going anywhere from, let's see, about single kW to hundreds of kW for steam generation. Why don't we go to the next slide? So there's been a number of demonstrations in large scale of high temperature heat pumps greater than 1 megawatt. District heating is a very common application, and industrial applications. And these are the manufacturers that have demonstrated in, again, above 1 megawatt. So there is some product availability, and current situation is we're going to have to bring product from overseas. Part of the project we're moving into is to reach out to these kind of vendors, and also to reach out to the Johnson Controls and other heat pump manufacturers in the commercial residential area that might want to move into this area. But you can see that at least we have these products that are very large and have been used in a number of applications. ACEEE has also been involved in an international energy project called Annex 58, where countries are sharing the current products out there, the current case studies. There's many hundreds of case studies of industrial heat pumps that have been documented. And we are digging into those and enjoying the sharing of that information in Annex 58. But you can see the delivery temperature is getting up there, up to, highs there, 174C. Usually we're talking currently around 100 and 120, but a number of these very high temperature heat pumps are being offered up. So that's really, if you remember the chart that Ed showed, that where all the waste, the process heat opportunity is. When you start getting into 150s, you can really start making a difference. Yeah, so here's product availability in Japan. And I think the slide speaks for itself. There's also a discussion around synthetic working fluids versus natural refrigerants. Natural refrigerants would be ammonia, CO2, water, butane, and as opposed to the synthetic refrigerants. It depends on the application that you're using, but of course, the natural refrigerants have very low global warming potential impact. Some of the synthetic refrigerants have a limited amount of impact, but that's kind of a raging debate in the industrial heat pump community of using the natural refrigerants versus not. I learned last week there's a number of states that kind of I don't say eliminate, but don't allow, but make the restrictions on using, for example, ammonia in your facility. New Jersey comes to mind. I think Illinois is another one. So that's something that we're going to have to dig into a little more, because we want as much flexibility in the type of working fluids that we can use. All right, so this is we came up with some bullets here to kind of probe your thoughts. You're probably thinking, is this right for my plant? Is this right for my company? And I think you want process heat less than 150 degrees C. It could be a little less than that, but I think at least that. Generally, you want a heat pump lift, and that's from the heat source to the heat sink of around 40 degrees C or less. Plant operating hours, at least 2,000, most likely 4,000. And do you have space for that heat pump? As Ed mentioned on the one chart, generally the economics are good when the electricity to natural gas price is less than 4. Of course, recently at $6 or $7 a million BTU, that ratio is looking better for heat pumps. The other point I want to make is, we've been networking with different countries, and when we talk to Australia, who's had an industrial heat pump program for about 8 years now, what they learned through actual application is when they look to apply the heat pump in different processes, generally in the food industry, what they found is when they were replacing out a boiler, the amount of losses that you were eliminating, it's not just the combustion efficiency of the boiler, but you're eliminating all the losses in delivering that steam to the actual application and the recovery losses of bringing the condensate back. And they found that the economics got a little better than they thought, because you could site and size the heat pump to the actual application in a more optimal way. I think that's it, Ed.
Okay, well, thanks,
someone?
Paul. I
Sure.
appreciate your dive into the status, the industrial scale. So just to wrap up here, we want to note that what we found is that IHPs can save upwards of 32% of the source energy process heat. So the source energy, again, accounts for the difference between natural gas and the amount of electricity that's needed. And at the unit operations level, the amount of impact can be significant. IHPs can have paybacks that are attractive, at least get you into the ballpark of conversations on capital expenditure. And the next big step here is field level pilots of industrial heat pumps in lots of different kinds of applications, different kinds of industrial groups, and in different regions of the country. That's the next phase that we're trying to push in our research. And I think this is also an opportune time to put out a challenge, a call to action here, to participate and to drive these pilots, because there's a lot that we don't know at this point in the US applications. There's a lot that we need to communicate as well. And this is an opportunity for engagement across not only DOE and AMO, but academics, national labs, manufacturers of industrial heat pumps, engineering companies, particularly important to think about for the integration. But we also need to educate the cadre of people that will look at industrial heat pump applications, utilize approaches such as pinch analyses, such as we did in our analysis. And Paul noted the international collaboration. That's really important to learn quickly from those that have been advancing this field for years. I mentioned earlier the workforce. We need workforce not only for the installation and the maintenance of industrial heat pumps, but for other applications as well. And of course, we need to also consider input on policies to help accelerate adoption at scale. So with that, I'll note that we've got some references and we look forward to any questions you might have.